Okay, so getting our back on our track here. So we have these following four main groups on the HR diagram, which map out the stellar evolutionary stages of stars that we see in the night sky. So most of the stars live on the main sequence. Okay, and so most of the stars we see in the sky are main sequence stars. Those red dwarf stars, of course, we don't see a lot of them because they're so dim, but there's definitely a lot more of them because they live a lot longer. Okay, we tend to see a lot of these brighter stars up here that are living out their lives a lot faster, eventually dying off as giants, and then the really massive ones dying off as supergiants. So we talked about solar mass type stars that went to try to burn their helium. They couldn't burn carbon and oxygen, so they left the giant stage, finally dying as a planetary nebula and then ending up as a white dwarf. So just to remind yourself, what forms in nebula regions like this? Stars! Okay? And then just to remind yourself once again, once a protostar starts fusing hydrogen into helium in its core, it falls onto the what of the HR diagram. Hopefully you said the main sequence. Okay, that kind of just gets you caught up. So now let's talk about those massive stars. Okay, stars that are, let's say, 10 times as massive as the sun. Now there is a limit that stars really can't withstand and create a normal star anywhere past about 200 solar masses. At that point, it's just too chaotic for that star to balance in terms of hydrostatic and thermal equilibrium. But massive stars, anything greater than about 10 times the mass of our sun, follows a pretty well understood death, okay? So these stars live out their main sequence life very quickly because they have a lot of mass and therefore they burn through that mass really, really fast, okay? So they leave the main sequence and join up onto the supergiant phase where they're burning their helium. They then go to the next level and they can get hot enough to start fusion of carbon, and then even get hot enough to do fusion of oxygen, followed by silicon, neon, sulfur, silicon, all the way down until it gets to iron in its core. Okay, so just like how we had the star expand out its outer layers while its core was contracting and then doing this kind of back and forth with the giant phase, the same thing happens in the supergiant phase, creating this onion-like star of all these different layers of fusion happening around the core. Okay, but now you can see, of course, since these stars are very massive, they're burning through their fuel very quickly, they can go through this in a relatively short amount of time. Now, it gets to the point where these stars can have iron in their core, but they never actually get hot enough to fuse iron. So iron exists in the core, but that core contraction just never gets hot enough that iron can finally fuse. Okay, so what happens? Once a star is this big, okay, and it wants to try to go to the next fusion stage, it just really can't withstand that pressure, okay? And the star essentially explodes outward into a supernova. The supernova is the expansion of all that gas withheld in that star. And so these are pictures of supernova explosion. So all that gas that was accumulated in the star life in terms of those thermonuclear reactions is now being blown out into the interstellar medium. Okay, that silicon, that sulfur, even that iron is then populated back into the universe. Now, these supernova reactions are so big that they actually do ionize a lot of these elements, causing more protons to be produced in high temperature environments, allowing for further fusion. And that is where we actually get the rest of our heavy elements. Okay, so this is where you really can say we're made of star stuff, because once these stars explode, all those elements are then populated back into the universe, which then create new stars and solar systems, and then eventually us. So that's where Carl Sagan is famously quoted of saying, we are made of star stuff. Okay, and that's because all the elements that you think of on the periodic table come from the explosion of stars. So once a supermassive star explodes out into the supernova, that core is still trying to contract, and that core can die in two ways. One, it can end up as what's called a neutron star, or two, it ends up as a black hole. Okay, so let's take a few moments to look at some of these beautiful images of supernova explosion. So here's a supernova in the X-ray, infrared, and visible wavelengths. Okay, here's a nice infographic that I'll let you read on your own, just kind of talking about the core collapse into a supernova explosion of these massive stars. So pause it if you want to read this more closely. Now I love this one. Okay, these are before and after images of supernova explosions. So in this one, we're looking at the spiral galaxy M81. We're looking at where the star is, and then when the star goes supernova. So let's look at this again. Where's the original star? Boom, goes supernova. Okay, and this boom, okay, this brightness that we can see from the supernova explosion, depending on the mass of the star. So lower mass, massive stars can last about, I think a couple days to a few weeks. But some of the really massive ones can withstand this brightness for a couple months or so. So it's not immediate that we have to look at them, but we have to look at them fairly quickly to see that aftermath. Okay, and then all that gas is then released out back into the interstellar medium. This is the remnant of a supernova. So after the supernova, like I said, it dies and that central core continues to contract, leaving behind one of two things, typically depending on the mass. Okay, the lower the mass one will end up as a neutron star. Those really massive ones, okay, end up as a black hole. So the neutron star, that interior ends up being very, very hot and dense and very tiny. Okay, so these neutron stars are being held up not by nuclear reactions again, but that same thing that white dwarfs are held up by, degeneracy pressure. But this time it's not the electrons around the central core of the atom, it's the neutrons themselves that are providing that degeneracy pressure, which keeps the shape of the star. Now, these have a lot of energy in a very small radius, and they sometimes have these beams of electromagnetic radiation coming out of the poles. So these stars are spinning, and sometimes that beam of radiation will come towards Earth and away from Earth, kind of like a lighthouse beam coming towards you and away from you. And when we see that, it looks like these stars are pulsing at us. Okay, so sometimes we call these pulsars. Okay, so a type of a neutron star is a pulsar. We can see that beam of light coming at us and going away, coming at us and going away. Okay, it's just a stream of charged particles. So the other, here's a good image of some pulsars coming from the Crab Nebula. Okay, so the other way a supernova, a really massive star, can die, okay, after all that gas is blown out in the supernova explosion, that center can result in the core collapse that gets down to a singularity point, to the point that all that mass goes down and all that density into a singular point, so massive that we create a black hole, where not only is matter bent, but the space and time itself are warped because of the amount of gravitational force surrounding it. So now I had to update this slide, right? Because typically we were only ever able to see black holes by looking at how interactions of materials around that death of a star take place. But we've recently, this year in 2019, finally produced an image. A group of scientists from around the world took a couple years to actually photograph in the microwave wavelengths the first image of a black hole. And it's not necessarily a discovery, but it's more of a confirmation of what we've mathematically and theoretically have thought that a black hole would look like. And these observations match what we have theoretically predicted, which is a great way to really show society that that is how science works. So black holes essentially have the center being so much mass and so dense at such a tiny little point in space that they can warp space and time around it. So not even light can escape. The light you're seeing from this black hole is the matter around the black hole at the event horizon being influenced by the amazing amount of gravity. Okay. So this is an overview of how these high mass stars will die. So take a moment and review this for yourself. Okay, so there's very distinct stellar populations, okay? So the stellar evolution that we talked about has produced two curious populations in our own galaxy. We have metal-rich young stars, which we call population 1 stars, okay? And we also have population 2 stars, which are members of the first older generation of stars, okay? So the first ones we call metal-rich stars, okay? Any element heavier than hydrogen or helium, okay? They're the members of a second generation of stars. Okay, our sun is relatively young, metal-rich, and we are what we call a population 1 star. Okay, but these metal-poor, these older stars, they were the first ones to form, so they're mainly made up of those hydrogen and have relatively few of the heavier elements compared to the newer stars. So we call these stars population 2 stars. And we'll see this when we come back to talk about the Milky Way and other galaxies later on. But the other important thing I wanted to bring up is that I've outlined these really nice evolutionary steps for massive stars and low mass stars. But it's not really that simple, because most stars exist in a binary system where 2 stars orbit around each other. And when 2 stars orbit around each other and one star starts to evolve, it can change the evolutionary tracks of its companion star. And this is due to the fact that they gravitationally can interact with each other and essentially share mass between them as one star evolves and another doesn't. Okay, so this dotted line is what's called the Roche Lobe. Okay, this is the gravitational boundary that if a star expands beyond that gravitational boundary, it can start to share its mass with its companion binary star. So here's a couple examples of different binary systems that can have stars at different stellar evolutions. And if one star starts to evolve, let's say we had a white dwarf star, next to a companion star that's continuing to evolve, that white dwarf could actually take on some of the mass from that evolving star and cause that white dwarf to start to live again, let's say. In this case, that white dwarf actually kind of becomes a star again, starts doing some nuclear reactions, but then blows up once again into what we call a nova, or a white dwarf nova, and then dying again as a white dwarf. But it gives that white dwarf star like another little birth. Okay, so stars are primarily in binary systems, and we can change the typical evolutionary track by the fact that these 2 stars can interact with one another. But if we went back to our simple scale, here would be a nice outline of the evolution of stars, okay, from our low mass stars to our high mass stars. So the low mass on the top and the high mass stars on the bottom, of how those stars will evolve and then eventually die. Okay, and that is the full stellar life cycle. So from the birth, the evolution, and the death of stars.